Good day, everyone. Welcome to Q-Chem webinar number 39. Today's speaker is Dr. Yuezhi Mao, and he speaks on a very popular subject. It's energy decomposition analysis in Q-Chem. Without further ado, let me introduce today's speaker. Yuezhi Mao got his BS in materials chemistry from Peking University. He went on to his PhD with Martin Hagborn here at Berkeley, studying density functional theory and its applications to intermolecular interactions. He is a major contributor of the second generation ALMO-EDA. Right now, he is working as a postdoc at Stanford with Tom Marklin. His current research focuses on adiabatic processes in gas phase and condensed phase electron transfer problems. Then I'm gonna turn this over to Yuezhi.
Okay. Hi everyone. It's thanks. I would like to thank Kuan Yu for the very kind introduction, and it's my pleasure to talk about this topic for the second time in Q-Chem webinar. And so our focus today is energy decomposition analysis, and it is a category of method which is able to separate intermolecular interaction energies into physically intuitive meaningful terms like permanent electrostatics, polarization, dispersion, and so forth. And the way to do this analysis is not unique, and there have been many perturbative or variational EDA schemes reported. And today, our focus is energy decomposition based on absolutely localized molecular orbitals. So these ALMOs, molecular orbitals on fragment, which are expanded by the AO basis functions of each fragment only. And under the molecular definition of charge population, these ALMOs will forbid charge delocalization between fragments, so we can achieve a separation between polarization and the charge transfer. These ALMOs are constructed from isolated fragment orbitals, and then we bring them together, and this energy change to form this unrelaxed frozen complex is called the frozen energy. And then we allow the ALMOs to relax with respect to the on-fragment orbital rotations. And this energy lowering is defined as polarization energy. And finally, we do a standard unconstrained SDF calculation, and the further energy lowering is assigned to charge transfer. And this is the original ALMO-EDA scheme. And in the last few years, we have expanded the arsenal of ALMO-EDA methods very substantially. And I would like to give an overview of this method in the present Q-Chem. And for more details about how this method work and how to set up the calculations, I would refer you to my previous Q-Chem webinar, also on the EDA topic. So first, I would like to talk about ALMO-EDA for single point Q-Chem DFT calculations. So we have second generation ALMO-EDA, which overcomes two limitations of the previous method. So first, we use these fragment electrical response functions to provide a useful basis set limit for the separation between polarization and the charge transfer. And we also enabled further decomposition of the frozen interaction into contributions from permanent electrostatics, polyrepulsion, and dispersion. So in the second generation ALMO-EDA, we have 5 terms: electrostatics, polyrepulsion, dispersion, polarization, and charge transfer. And this is an example we showed in our original publication, which is this adenine-thymine complex. And for the hydrogen bonded configuration, this interaction, by doing the ALMO-EDA, we can show the interaction is dominated by permanent electrostatics, with also non-trivial contributions from all the other components. While for the stacked configuration, this interaction is dominated by dispersion, which is not a surprise, but it's also followed by quite significant electrostatics. And this ALMO-EDA for Q-Chem DFT has also been extended to bonded interactions, and which needs some slightly different treatment. And this work was done by Dr. Daniel Levine, a former member of the Hadagarden group. And for the bonded EDA, we start from 2 high-spin fragments. I mean, for the single bond case, we start from 2 high-spin restrict open shell fragments. And we construct the triplet frozen state, which is also high-spin. And here there is a new term called preparation energy, which includes the geometry distortion, which can also be computed in the non-bonded EDA, and also the orbital rehybridization, which can be understood as the electronic preparation of each radical fragment to form a chemical bond with a specific atom. And then we have also this new term, spin coupling term, which describes the energy change upon the spin flip from the high spin frozen state to the low spin. So it transfers from a triplet to a singlet. And then we can, similar to the non-bonded EDA, we can also calculate polarization and the charge transfer using the Yamaguchi spin projected wave functions in the low spin state. And using this bonded EDA, the authors of this paper investigated several metal-metal bonds, which are interesting in inorganic chemistry. And so they found this metal-metal bond have quite different characters. So for this magnesium bond, it's fully dominated by this spin coupling term. So it's a typical nonpolar covalent bond. While for the zinc bond, although this SC term is still very large, there is also a non-trivial charge transfer contribution. So we say it's primarily covalent, but with also notable ionic character. And for the manganese bond in this complex, the charge transfer strength is almost comparable to the spin coupling, and it's a typical charge shifted bond. And this bonded EDA feature and also the documentation will be available in the 5.3 release of Q-Chem. And ALMO-EDA has also been extended to correlated wave functions and also excited state calculations. And for correlated wave functions, the representative is MP2 theory. And the MP2 EDA can be viewed as a combination of Hartree-Fock EDA and the decomposition of the PG2 contribution to the binding. So the Hartree-Fock EDA can be separated into frozen polarization and charge transfer as in the original ALMO-EDA method. While for the PT2 decomposition, there is an extra term, which is a dispersion here. And this MP2 EDA has also been extended to restricted open shell MP2 recently to treat radical molecule interactions. And the key to the MP2 EDA is the partition of these double excitations in the MP2 equation. And so here also for the restrict open shell MP2, because the non-beryllium singles are non-zero, so we also need a partition for the singles amplitude. And here the type 1 and the type 2 are the so-called charge conserving double excitations. So for type 1, everything is fully located on a single fragment, so it's related to frozen and polarization. While for type 2, it's typical dispersion type of correlation, and this type 3, apparently it is charge transfer. And we used this ROMP2 EDA to investigate this interaction between the halobenzene radical cation with water, and this halobenzene radical cation can form either ionic hydrogen bond or halogen bond. And we see that moving from the top to the bottom along this halogen column in the periodic table, this ionic halogen bond becomes more and more favorable than the hydrogen bond. And this trend is results from multiple components, including polarization, dispersion, and charge transfer. And ALMO-EDA has also been extended to TDDFT with the Tamm-Denkoff approximation to treat complexes with excited state molecules. This is particularly useful for two types of scenarios. The first is we want to investigate how the environment modulates the molecular excitations, such as the famous solvatochromism phenomena. And second, there are some complexes which are only weakly bound in ground state, but they are much more strongly bound in the excited state. These are called like aximers, and these sometimes it's useful to separate the stabilization caused by excitonic coupling and charge transfer. And so for a given excited state kappa, this interaction energy in this excited state can be separated into these terms. And for the frozen polarization and the charge transfer, they can be, like in the MP2-EDA, they can be viewed as a ground state contribution plus the shift in excitation energy caused by the corresponding energy component. While this excitonic splitting term is a excited specific phenomena, it describes the energy splitting caused by the in-phase or out-of-phase coupling of the fragment excitons. And also for this first scenario here, like a chromophore immersed in solvent, because the excitation is mainly localized on this chromophore, so one can simply drop this excitonic coupling term. And this method has been used to investigate some aximers. Here is an example of the first excited state of the pyrroline aximer. And this is a B3G state, which comes from the out-of-phase combination of each pyrroline fragment's first excited state. And if we look at the energy decomposition, first we notice it's indeed very strongly bound in this excited state, because please note the energy scale here is in EV, so it's a very strong binding. And also charge transfer makes the largest contribution to this binding in the excited state. And the excitonic coupling term decays much slower than charge transfer, so it crosses with the charge transfer beyond like 4 angstrom, and then it becomes a dominant binding force in the long range. And the third category of method is the extension of ALMO-based method to analyze like molecular property shifts induced by intermolecular interactions. And this method is called the adiabatic EDA, and it can be understood through this plot. So the energy decomposition I just talked about can be regarded as vertical EDA, corresponding to this dashed line here, because it's performed at a single given geometry. Typically, it's optimized geometry on the fully relaxed potential energy surface. However, in adiabatic EDA, we do things slightly differently, and we relax a complex geometry on each of these intermediate potential energy surface. Then we calculate the energy components using the difference between these minima on each potential energy surface. And more importantly, by doing this relaxation on each PES, we are able to easily partition the shifts in structural and vibrational properties into the contributions from these different components, which turn out to be very useful. And here is a proof of concept example of this adiabatic EDA, which is water chloride complex, and we optimized the geometry and did frequency calculation on each of these potential empty surface. And we are able to find that this near linear hydrogen bond and also this significantly redshifted OH stretch frequency are consequences of charge transfer. Okay, so yeah, for the methods I just talked about, as I said, you can find probably more details in my previous webinar. And now I'm going to talk a few more advances in the recent 1 or 2 years, and they are not covered by my last webinar. So the first thing I would like to talk about is a more robust scheme for unrestricted ALMO-EDA. And this is mainly to solve a problem posed by like a highly symmetric radicals, because like we found something strange by running the EDA for this water fluorine complex, which is the fluorine is a radical here. And if you align this molecule differently in the XYZ coordinate, you will get different EDA results. And we look into this further and find that this fragment calculation for this F dot will always have this unpaired electron along the Z-axis. But I mean, these fragment electronic configurations are cannot be distinguished at the fragment level, but these two configurations are no longer degenerate in the supersystem when this water is present, and they correspond to the A prime and A double prime states. And yeah, so it's better to resolve such ambiguity in the EDA results. And we proposed a scheme called polarize and depolarize to get the unique definition and for the frozen state. So the idea of this approach is to make use of the polarizing effect of the water molecule to break the degeneracy. So first you start from these initial frozen states constructed directly from the fragment orbitals. And then from here, you launch a full polarization calculation with SCF-MI. And hopefully you will be able to get a unique solution for SCF-MI because this polarization effect will break the degeneracy. So you should be able to converge to a stable solution here. And then we use each block of this ALMO matrix as the initial guess for a new set of fragment calculations. And to make sure that these fragment electronic configurations resemble those in the polarized wave function, we use a maximum overlap method for these fragment SCFs. And then we can get, by concatenating these orbitals, we are able to get a finalized frozen wave function. And this approach turned out to work very well. And so with these two differently aligned water fluorine complex, we are able to get the same polarized state, and then with MOM, we are able to get the same uniquely defined and also energetically favorable frozen state. So now we don't have this ambiguity in the EDA result. And here is an input example for this more robust uALMO-EDA, and this is for a formaldehyde hydroxyl radical complex. And so for this complex, the energetically more favorable frozen state is in this A double prime state, where this unpaired electron is perpendicular to the molecular plane. However, if you just run a second generation ALMO-EDA calculation without any special treatment, you will find your frozen state is actually in this A prime state. And to ensure that the energy decomposition is performed always on the most stable state, we use this new variable EDA align fragment spin. We set it equals 2, and this will apply this polarized and then depolarized scheme to resolve this ambiguity in the definition of frozen state, and it will also perform a wave function stability analysis and correction in this polarization calculation launched from the initial frozen calculation. And this turned out to be important to make sure the polarizing step is actually doing the thing we want. And the second most recent advance is like the variational forward-backward charge transfer analysis. And the goal of this method is to decompose the charge transfer effect into the forward and backward contributions. And in Q-Chem, there used to be this perturbative charge transfer analysis, which is basically taking a Rutan step from the polarized wave function. And the Rutan step corresponds to a single diagonalization of the Fock matrix. And by some reformulation, you can partition that into the forward and the backward contributions. And the residual compared to the full variational charge transfer result is regarded as a high order effect. And so our new method is slightly different. Instead of using the perturbative Rutan step, we define like two one-way CT states using a technique called generalized CFMI. So we still start from the polarized ALMO state. And then, so if we want to get the forward-only charge transfer, we modify the variational space for fragment A to allow it to be able to relax into the full virtual orbital of the system. While for fragment B, we keep it absolutely localized. So this will be able to capture A to B charge transfer as well as the response of fragment B. And for the backward charge transfer, we can do something similar to define this another one-way CT states. And then the forward and backward CT energy can be simply be defined as the energy difference between these intermediate states and this original polarized state. And one main feature of this method is these two one-way CT states are variationally optimized, so it's very easy to compute the associated nuclear forces. And so these two states can be seamlessly integrated with the adiabatic EDA approach. And we can separate not only energetic effect, but also the effect on observables. So use this method, we looked at this ruthenium dinitrogen complex. So first we look at the energetics, and we find that for this system, the forward and backward CT have very comparable contributions because they both basically like lie halfway between the polarized state and the fully relaxed state. And if you look at the COVPs for the forward and backward donation, for the forward donation, it's the sigma donation from the lone pair of this nitrogen to the empty d orbital of the ruthenium, and for the backward donation, it's from the occupied d orbital of ruthenium to this pi star orbital of nitrogen. And moving to molecular properties, here we are looking at the change in the bond length and vibrational frequency of the N2 molecule, and quite different from the energetics picture. We find that the signature like redshift and the bond elongation only appear when you turn on both forward and backward charge transfer. While for energetics, we actually find the forward and backward contributions are quite additive because they are both like halfway between these two. And here, there is a very significant synergistic effect because only when you have the two at the same time, you get the significant redshift and the bond elongation. And here is a Q-Chem input for this variational forward-backward analysis for this carbonyl beryllium oxide complex. And the setup of this calculation are very simple, actually. So besides doing the standard optimization and the followed frequency calculation, you only need to specify this one rand variable VFB CTA. And if you write forward, it means the charge transfer. You are considering the charge transfer from fragment 1 to 2. And if you write backward, it's the opposite. And the third recent development is we make ALMO-EDA compatible with implicit solvent models, including PCM and the Minnesota solvation model SMD. And so the overall scheme is described by this diagram. What we are trying to decompose is the energy difference between these fully solvated complex and the sum of the solvated fragment, the sum of energies of the solvated isolated fragment. And as usual, we can partition that into frozen polarization and charge transfer contributions. And the frozen contribution can be further partitioned into this new term delta E sol and also a so-called vacuum frozen interaction. This vacuum frozen interaction is a frozen interaction evaluated as in gas phase, but with the orbitals optimized in solvent. While this new term delta E sol describes the gain or loss of the solvation energy upon the formation of the complex, because for the complexations for the complexation process, it changes from many separated cavities into this one integrated cavity for the full complex. So the solvation energy must be changed. And then we can perform SCFMI and full SCF calculations under the solvent. Then we can define the polarization and the charge transfer contributions as before. And the main feature of this scheme is solvent effect is accounted for in each intermediate step of the energy decomposition analysis, which differs from how many other EDA schemes treat the solvent effect. And here is an example, which is a water sodium complex in PCM water. So this part is exactly the same as like the standard setup of an EDA2 calculation, but you just need to specify the solvent method to PCM, which is like how you run PCM for a standard single point calculation in Q-Chem. And then also you need to specify the dielectric constant for your solvent. Here it is water. And this will be the result section of this calculation. And you can see this new term, E sol, and also the so-called vacuum frozen energy. You can actually combine them as a frozen energy in solvent. And I would also recommend the combination of this solvent term with classical electrostatics, because in the long range, the only effect of the solvent is to damp the long-range electrostatic interaction, which can be understood simply through the Coulomb's law in dielectric. And the last new feature I would like to mention is ALMO-EDA for complexes involving fragments in non-aufbau electronic configurations. And this is actually still under development, but some of the features can already be used in some special cases. So the motivation of doing this is is in many complexes, such as those involving transition metals or like radicals such as carbene can have different, most stable electronic configurations at different stages of the EDA calculation. So this is an example reported by Franking and co-workers, and it is a barium plus CO complex. So in the isolated fragment state and also frozen and polarized state, the most stable electronic configuration of barium plus is the 6s1 configuration, which obeys this off-ball principle. But in the full SCF state, it turned out that the most stable electronic configuration for the barium plus is 5D one. So this is promoted to the 5D orbital. And actually for energy decomposition calculation, currently it only makes sense if each state is in the same electronic configuration, or we say manifold. So we need a way to actually perform the energy decomposition analysis consistently in this state, which is non-aufbau at these stages. And what we do is we combine MOM, the maximum overlap method again, with ALMO-EDA. And so we prepare non-aufbau fragment SCF solution using MOM and construct the frozen state using this A star with a ground state fragment. And then we can apply MOM in the following SCF-MI and the full SCF calculations to ensure the polarized and fully relaxed wave functions are also in the desired electronic configuration. And here is the input for the system I just mentioned, the barium plus CO complex. And to do this calculation, you need this RAM variable EDA2 MOM equals true. And then we need to specify the orbital as occupied virtual swaps to define this non-aufbau electronic configuration. And it's done through this SCF-MI MOM section in the Q-Chem input. And the format is, first entry is for fragment index. So here is for the barium plus. And the second and the third number for HOMO minus X and LUMO plus Y. So 0, 2 means HOMO to LUMO plus 2. And the last entry should be lowercase a or b for alpha and beta spin. And by default, it's doing alpha. And so we performed ALMO-EDA on these two electronic configurations for the barium plus. And the preparation energy here describes the energy required to promote the 6s to 5d for the isolated barium plus. So it's actually quite a substantial number. However, this energy loss is compensated by the much more favorable charge transfer energy when the barium electron is in the 5d orbital. And this is further confirmed by the dominant COVP in this complex. And you can see the 5D1 to the pi star donation has contributed significantly to the energy lowering. And this barium plus actually in this fully relaxed complex behaves like a transition metal. And now I would like to give you some ideas how ALMO-EDA can be used to facilitate chemistry studies in different aspects. So the first application of ALMO-EDA is to unravel the nature of chemical bonding, which sounds like the original objective of this method. So this is a study by ourselves. It's about blue shifting hydrogen bond in these fluoroform complexes. And because for most common hydrogen bonds like the water dimer or the water chloride complex we just talked about, the hydrogen bond, the hydrogen bond will be redshifted. This sigma bond for the hydrogen donor will move to like a lower frequency. And however, for these complexes, this CH bond is blue shifted. Its vibrational frequency becomes higher, and we would like to understand why. And by doing this adiabatic EDA, it's immediately clear that polarization and charge transfer should not be the reason for that, because the maximum blue shifting is achieved on the frozen surface. And then we did a further decomposition of the force analysis of the force along the intermolecular force exerted on this hydrogen along this CH bond. And we found that among the three components of the frozen interaction, only the polyrepulsion wants to shorten this bond. And the bond shortening is always associated with blue shifting in these complexes. So we assign the reason for the blue shifting to polyrepulsion. And we also need relatively weak charge transfer, because if charge transfer is very strong, then it's going to compensate for the blue shifting frozen interaction. The charge transfer is the main reason for the red shifting in commonly seen hydrogen bonds. And this is another study by other people for halogen bonding with pi systems. So here is halogen bonds formed by the BRF molecule and a pi system. Here it is Naslin. And there are two different binding modes. And they also used adiabatic EDA. And interestingly, they found that the correct ordering of the relative stability of these two binding modes can only be reproduced when charge transfer is present. And if you remove the charge transfer, the relative stability will be the opposite. And ALMO-EDA can also assist study of organic chemistry to decipher the role of non-covalent interaction in modulating chemical reactivity. And this is this is from a recent publication of the Hartwig group at Berkeley, and they are trying to design some catalyst for the anti-Markov-Nikov hydroarylation reaction between the benzene and alkene. And this reaction is catalyzed by this nickel complex. And what they found is when the nickel complex is having bulky ligands, higher reactivity can be achieved. And they think there must be some like a non-covalent interaction into play. So they did ALMO-EDA for this triple delta E. So the first delta is for the interaction energy between this ligand, which is a carbene, and this nickel containing moiety. And the second delta is for the difference between this reductive elimination transition state and the ground state. And the third delta is for the difference between the two different ligands. And they found that this bulkier ligand is gives a more favorable transition state, and by almost like 7 kcal per mole here, and 2.4 comes from like less unfavorable geometry distortion, and the rest comes from non-covalent interaction. And if you do the ALMO-EDA for this difference, the triple delta E, you will find that although the bulkier ligand has a larger polyrepulsion, which is not surprising, but it's actually more stabilized by other forces like electrostatics, dispersion, and charge transfer. And by doing this kind of analysis, it can provide some insight into the design of like the ligand in this catalyst, which can give you like a energetically favorable transition state. And ALMO-EDA can also assist force field development. And previously, we compared the original amoeba force field, the terms in the original amoeba force field with the counterparts in ALMO-EDA, and we found that almost for each of these components, the agreement is not so great. For example, for the permanent electrostatics in amoeba, it's less attractive than the ALMO-EDA results across the board, and this is because the lack of account for charge penetration effect. And so the accuracy of the force field relies on the cancellation of errors in different components. For example, it needs to soften this van der Waals potential to account for the missing short-range effects such as charge penetration and charge transfer. And most recently, the Teresa Helgauden group in Berkeley trained and validated a new many-body potential for water, which is called MBUCB, and using the data of ALMO-EDA. And from these plots, you can see they are able to achieve a much better agreement in each of these energy components than what is shown in these plots. And yeah, now I would like to talk about some basic job control for DFT-based ALMO-EDA before we do some demonstrative examples. And so if you have used this EDA tool in Q-Chem, you would probably already know there will be some option sets available to make things easier. So for option 1, it's frozen decomposition plus perf DQ polarization. For option 2, it's also frozen decomposition, but with original ALMO polarization. And I would like to note that EDA2 will be used as a default, has been used as a default EDA driver since 5.2 release. And now if you simply type job type equals EDA without specifying any EDA2 RAM variable, it will run through the EDA2 equals 2 with perturbative charge transfer analysis. And some general recommendations. First, always use dispersion corrected density functionals for the calculations for non-covalent interactions, because otherwise the interaction energy will be not reliable and the dispersion terms given by the ALMO-EDA is not meaningful. And so for the choice between these two options, I think for small to medium systems, if a large basis set is affordable, you should consider use option 1 to get a more legitimate separation between polarization and charge transfer. While if your system is already very large and only double zeta basis sets are affordable, then you can use option 2, because for double zeta basis sets, these two schemes will give very similar result usually. And there are also some other useful control commands. So this EDA PCTA equals true will do the perturbative charge transfer analysis. And the EDA BSSE is for doing counterpoise correction for the interaction energy and also the charge transfer component. So maybe you should use this when you use a small basis set. And this one, EDA classical dispersion equals true. And this will calculate the dispersion energy using the unmodified fragment densities, unlike the orthogonal density in the orthogonal frozen decomposition. And this is particularly useful when there is ECP, the pseudo potential, because when there is ECP, Q-Chem will disable the orthogonal decomposition. And if you still want to see the dispersion contribution, you should set this to true. And the last one I would like to mention is the frozen relax. If you set that to so currently, if you do a unrestricted ALMO-EDA, it will automatically do this polarize and depolarize scheme by default, but that sometimes will also increase the computation cost. So if you are confident that your radical doesn't suffer from the degeneracy electronic state problem, then you can consider turn this off, which can save you some computational time. And we also provided many useful visualization tools in EDA2. And the first thing is COVPs for the donor and the acceptor orbitals in charge transfer. And so the prerequisite for COVP analysis is a perturbative CTA. And in EDA2, we also implemented an automated scheme to generate these COVPs, which I would show later. And we also offered the electron density difference plots, which can be triggered by this RAM variable, and it will plot two different densities. So the first one is the density change upon polarization, and the other one is the density change due to charge transfer. And for unrestricted cases, we will also plot the density, spin density in all these three intermediate states. And we also implemented the natural orbital for chemical valence, the NOCV analysis, which is a scheme proposed by others, but it's quite compatible with ALMO-EDA. And NOCVs are eigenvectors of this density difference density matrix, and they appear in pairs with opposite eigenvalues. So the energy lowering associated with each pair of NOCV can be calculated using the so-called extended transition state method. And this can be turned on by set EDA NOCV equals true. And at last, we also enabled plots for the frozen and polarized ALMOs, which are directly from those block diagonal MO coefficient matrix. And for adiabatic EDA, if you want to do geometry optimization on the frozen or polarized surface, it's quite simple. Besides doing job type OPT, you'd only need to set these RAM variables into true to tell the code which PES the geometry optimization is performed. And for these two surfaces, up to first derivatives are supported. So for frequency calculations, they need to be done with finite difference, and this can be trivially parallelized. And so for adiabatic EDA, if you want to run the result for all surfaces, I will recommend to start from the fully relaxed surface and then turn off charge transfer and polarization step by step. And when you are this is a little tip, when you are using a functional like omega B97X-V, by setting this RAM variable to false, it will save a lot of time in the calculation of the force on the frozen surface. And also for unrestricted systems, such as those complexes with hydroxyl radical, it's very common you find your optimization is done on like a different electronics configuration than you thought about. And so for these kind of systems, if you want to make sure your adiabatic EDA is performed on the energetically stable surface, you can consider starting the calculation with a single point calculation with stability analysis and the correction, and then read in that as a guess for the first round of the geometry optimization. And now I will show you some demonstrative examples through the terminal, and I will show the vertical and adiabatic EDA for this complex I talked about already. And so first I will do adiabatic EDA, to determine the CO bond length and the stretching frequency of the CO on each of these surfaces. And using the fully optimized geometry, I will do a vertical EDA calculation and plot the COVPs and the electron density difference. And so to run these calculations, it can make life easier to use some scripts. If you don't want to write your own script, you can download mine from my personal GitHub. And now let's go to the terminal. So I hope everyone can see the screen. And so by using the script, we can set up the input for doing the adiabatic EDA, which can be set up by doing this command. Basically, first you start from two files. One is the XYZ file, which is a simple XYZ file, and also a file specify housing's partition. And this is specific to my script, of course, so you have different ways. So here it means the system has total charge 0, total multiplicity 1, and the charge on each fragment both 0, and the multiplicity for each fragment is both 1, and each fragment has 2 atoms. So that's a partition. And by running this script, you can find this input file under this adiabatic EDA folder, and it actually contains 6 Q-Chem jobs. So we first do geometry optimization on the fully relaxed surface and do frequency calculation. And then we move to the polarized surface. Here we have pole geometry equals true, and do frequency as well. And then we move to the frozen surface and do the same again. And if you run, after you run this calculation, you have output for these 6 Q-Chem jobs. And I do have a script to parse the necessary geometry and frequency information. So we can do that through get geom_freq, and for the adiabatic EDA folder, and do frequency, and tells that we are doing adiabatic EDA. If you run this, and you will get a bunch of CSV files, which can be, first you have the folder called geometry, which contains the structure optimized on each of the potential energy surface. And you can also find the frequency information, and this highest frequency correspond to the CO stretch. And from top to bottom, these 3 corresponds to the full SCF, polarized, and the frozen surface. So you can see it's blue shifted on the frozen surface compared to the isolated fragment, and then it's more blue shifted, and then moved to the right side, red side a little bit when charge transfer is turned on. And you can also find the information about the CO bond lengths, which are parsed by the script. And you can see the bond shortening is accompanied by the blue shift. And then we move to vertical EDA. Again, we use a different script to set up this. This is pretty long. And after running this, we get a vertical EDA input under this folder. And so this time we have this standard input for EDA2 equals 2. And then because we are doing the COVP and difference density plots, we are going to add a bunch of ramps to do that. So we have EDA PCTA equals true, which is for COVP, and also EDA COVP equals true, EDA print COVP equals 2, which triggers this automatic generation of COVP. And also we want to do difference density plots. So yeah, and so for doing the plots, we still need, So for doing the plots, we also need to give the information about the grid we use to plot this molecule. And with the new format of Q-Chem's plots section, we can simply do grid points. And we can use this command to specify the number of grid on each direction. So I give 100 to each of them, which is pretty dense. And by running this calculation, you first get an output, which is a standard EDA2 output, and you can find the basics here: the frozen, polarization, charge transfer, total interaction, and 2 different ways of doing the frozen decomposition. This is orthogonal decomposition, and the classical version is classical electrostatics, modified Pauli, and the same disperse energy here. And we also did the COVP analysis. So we should look at this section, the COVP analysis, and we can find the code automatically assigned these ones as the important COVPs, and because they are associated with the largest energy lowerings, and we want to visualize them. And they can be found from this folder, also in your working directory. And you can plot these cube files with iCubeMod. So you for the COVP 1 and 2, for example, and 1 is a donor orbital and 2 is an acceptor orbital. You can, because it's the empty acceptor orbital, we make it like a so this is like the first set of COVP, and then COVP 13 and 14 will correspond to, so this COVP correspond to the donation, the back donation actually, from the barium oxide to the pi star orbital of the CO, while for COVP pair 3 and 4, it corresponds to the same orbitals but perpendicular to these 2. And for the charge transfer in another direction from CO to the barium oxide, and we can also plot the COVPs, and you can show that it corresponds to the sigma donation actually. So we also make this acceptor orbital transparent. So yeah, so this is another pair for the CT from another direction. And for the difference density, it can be plotted in a similar way. And for difference density, probably you want to use a smaller ISO surface value because it's smaller. It's of smaller magnitude. So this is the density change when polarization happens. So by doing this, we can go back to the slides, and so all the results are collected here, and probably you can find your own system for non-covalent interactions and use a similar procedure to study the nature of these interactions. And yes, this is my talk, and I would like to thank Professor Martin Hedgarden for leading the development of ALMO-EDA, and I would also like to thank all these Martin Hedgarden group members, the former and the present members here, and who have made significant contributions to the EDA ALMO-EDA family of method in Q-Chem. And I would also like to thank Professor Teresa Hedgarden and Yihan Shao for many useful discussions about EDA schemes and applications, and Professor John Herbert and Dr. Ji-Chang Yu for a lot of improvement of the Q-Chem routines for implicit solvent and plotting, which makes these things much easier to work with. And I also would like to thank Q-Chem for giving me this great chance to talk about this energy decomposition again. And I hope I could convince you to use that in your future research. Thank you for your attention.
Yeah, thank you, Yuezhi. It's very informative and very useful presentation. We got several questions. The first one is regarding ALMO-EDA for TDDFT. Is it the combination restricted to closed shell system, or is it possible to do the triplet state or high spin state?
That's a good question. I think currently it's restricted to the singlet state and the TDDFT TDA, but yeah, it is possible to extend that to triplet state with the same theory. And I think we haven't implemented the open shell for TDDFT yet.
I see. Cool. Is it possible to do the salvation method with a TDDFT ALMO-EDA?
I think it's definitely possible, but yeah, but that will require something slightly more complicated, because there are actually, if you look at the Q-Chem menu, there are many different ways to account for the solvent effect in these excited state calculations. There are like LR and the state-specific method, and we need. So this is a. I mean, it's probably a new direction we should look at, but yeah, and we definitely need to think about how we are going to do this.
Cool. This question, the next question related to PCM. So why is the incorporation is mainly based on the frozen term, which is electrostatic, poly, and dispersion? Why, but doesn't explicit in the polarization, because the polarization is intrinsic in the solvent.
Yes, so I think the solvent, in fact, in the polarization and charge transfer, those two variational steps will play a role in the variational optimization in those calculations. And but the term I just mentioned, the delta E sol, is mainly for the cavity change. This happens as soon as the complex is formed. So that's why we stuff that term to the frozen interaction.
Thanks. So we have attendee. Can you elaborate more about the triplet delta EDA calculation?
Triplet. I think
the triple delta E calculation.
Oh, okay. This one. Okay. Oh.
Was it done the same way in Q-Chem as presented?
It is done in Q-Chem, yes, and I think I did read through the SI of that paper, and yeah, there is nothing special there, but you basically just need to take a lot of differences for the separate calculations. For example, you need to do transition state and the ground state for both ligands, right? And so then I think I think by doing 4 calculations, you can already get these triple delta E's. So you need to do EDA for, so the first delta is just for the interaction energy. So for every example, we have this delta, which is, so here it's the interaction between this carbene and this nickel containing moiety. And then we take a difference between the transition state and the ground state. So these two structures are just a transition state. I didn't show the ground states here. And also we need to take the difference when you use between the result of the different ligands. So so they are basically by doing 4 EDA calculations, you can generate these results.
Cool. The second question from the same attendees. So what is the best case to incorporate adiabatic EDA, since it seems that this method can be applied to all systems to get more precise results?
I would not say it gives more precise result, but it gives like a complementary view for these interactions. First, so if you go to the adiabatic EDA, like examples here, so so I think the main feature of this method is it's able to offer information about the molecular property changes, which can be done with vertical EDA. And also, by doing adiabatic EDA, you can also get the energetics information for the frozen polarization and the charge transfer, and these numbers will look slightly different from what you get from a vertical EDA. For example, for a strong like charge transfer complex, the frozen interaction, because it's performed at the fully relaxed geometry, it usually can be quite repulsive, and what you can learn from there is there is a strong polyrepulsion, while with adiabatic EDA, the complex will not be in, like the fragments will not be in close contact at the frozen surface if you optimize the geometry there. And then you get basically a usually it's a small attractive term. So the view for the interaction energy will be quite different. And but I would say the most important feature of the adiabatic EDA is the ability to investigate these molecular property shifts.
Cool. So the next question is, have you tried the ALMO-EDA with the system has multi-reference nature?
I think not yet. That's currently, I think it's a direction I think the Head-Garden group is thinking about. They can probably bring some method developed there, like couple cluster valence bond and some other method into the concept of EDA. And currently our things are mostly DFT-based. Also, the single bonded EDA is, I mean, it's also kind of multi-reference because it's done through a spin flip from the triplet reference and then with Yamaguchi spin projection. And yeah, there can be other ways to do energy decomposition with multi-reference.
I see. So we have more questions. So if you have an ambiguous system, how do you fragment them into, do you have any case for that? So it's hard to partition the system into two.
So I think there are definitely cases, yes. I mean, this is also an active field for research, which is so-called intramolecular EDA, rather than dealing with intermolecular interactions. And because, for example, you have like a aromatic system, and you have, or maybe you have just like a alkane chain, and there are some functional groups attached to that, and you want to study the interactions between these groups. We are thinking about doing like an ALMO version of intermolecular EDA, and that is still under development. Currently, we are mostly focusing on intermolecular interactions. And one special case is the bonded EDA again, but we still break this bond to treat that as intermolecular.
Cool. Thanks. So next question. So we have closed shell system with halogen bonding complex using 6311G ***. Would you recommend option EDA1 or EDA2?
I would say if your complex is not large, probably it's better to change to a like a triple zeta basis with diffuse function, then you run the calculation with EDA option 1. But if that is not affordable, I would suggest doing 631, doing this smaller basis set, probably with EDA option 2 is enough, because there in this 6311G ***, there is no diffuse function. So basically, the first calculation will give not much different results than the original ALMO scheme.
Thanks. And is it possible to use res RI for ALMO-EDA calculations?
For, you mean, so for this case,
the basis.
I think certainly yes, because the ALMO-EDA scheme is sort of independent from the technique to construct the Fock matrix. So because in both SCF-MI and SCF, there are you need to build the Fock matrix at each SCF iteration, and these Fock builds are done in the same way as the standard SCF. So if you do things like RIK, I think things can be speed up by quite a bit. And also for the MP2 EDA, it's done only for the RI version of MP2. Probably I didn't emphasize that. So it's only for RI MP2.
Thank you. The next question related to COVP.
Yep.
And you said it sounds quite similar to PD2 analysis from MBO theory. Can you make some comments on this?
I think that is true. I think the philosophy is similar, but the way of achieving these orbitals are quite different. So for MBO, as I know, they generate the Lewis orbitals first, and starting from the Lewis orbital reference, which containing all these occupied and valence virtual and Rydberg virtual orbitals, then they calculate the PT2 energy using this singles perturbation theory. And for COVP, we start from a variationally optimized ALMO state, and then we take a single Rutan step. And this Rutan step is reformulated with this Carley transformation, and so that's how we achieve and then we transform the diagonalization of the Fock matrix into the amplitude equation, and then by partition the amplitude into by partition the amplitude matrix into fragment blocks, and then perform SVD on the off-diagonal blocks. That's how we do generate these COVPs. And yeah, but because I have to say I haven't run the MBO results myself, so I can't really comment on how these orbitals will look different. But the way of generating them, the reference state are very different. So there might be some difference, but they are both able to give, I think, similar insights about these donor-acceptor interactions. And also, I think NBO tends to give very large charge transfer energies because of this reference state is the Lewis orbital reference state is not variationally optimized, and there have been many discussions in the recent years about the charge transfer energy produced by NBO theory.
Thank you. So I have last questions. Given that there is already has SAP analysis, can you make some suggestions about when one should use ALMO-EDA rather than SAP calculations?
Yeah, so I think currently the SAPT method is mostly limited to dimer systems. Also, there must be some extensions, but not widely used yet. And also, I think for the accuracy of intermolecular interactions, we have benchmarked quite a bit about ALMO-EDA versus SAPT, and we found that with combinatorially designed functionals like omega B97X-B or M-B, these functionals, the interaction energies can be even more accurate than the SAPT DFT theory, definitely more accurate than SAPT 0, and it's comparable probably to the SAPT 2+3 classes of method. And I think the energy decomposition in SAPT becomes a little bit entangled when you go to the higher orders. And so I think probably ALMO-EDA is still it gives results that are easier to interpret and also guaranteeing good accuracy for the interaction energies in general.
Thank you. Let's see. Don't have any more questions here. I'm gonna close out here. And thank you again, Yuezhi.
Thank you very much. Thank you.
If you have questions later, feel free to contact me. I'd like to first thank all the attendees for listening and participating. And please give us your feedback. Really appreciate it.
This concludes our webinar. We would like to thank Quan Yu Lu for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.